Let us check the question number 21. Same current I flows into parallel conductors distant 2D as shown. The strength of magnetic field at a point P equidistant from both the conductors is how much? The question is that, and 4 options as usually as given. First option is mu naught ID by 4 pi a. Of course, a is the distance to that point what has been mentioned. And of course, 2D is the distance between the parallel conductors carrying currents. So the second option he has given mu naught ID by 2 pi a. And option number 3, that is mu naught ID by 4 pi a square. And fourth option is mu naught ID by pi a square. So 4 different options he has given us. Out of them, which one is the correct option there, we just have to look into. So according to the problem, let us go by the figure what has been given first. He is just giving us 2 different conductors. Of course, these 2 are perpendicular to the board like we have to consider, and the distance of separation between these 2 is given as 2D. This is what has been mentioned there. And at a distance say A from each conductor, there is a point considered as P. And he has mentioned very clearly this distance as A and this distance also as A. They are at equal distance, of course, he has given. The point is at equidistant from both the conductors, that's what has been mentioned. And we know pretty well this is the point P. This total separation is 2D means this distance now becomes D and this distance now becomes D. That is what has been given as the figure there. Since the distances are equal, this angle he has mentioned it as alpha, this also he has mentioned that one as alpha. So these 2 angles are equal, these 2 distances are equal, and obviously magnetic field produced over there due to these 2 currents also will be equal. So if I consider the magnetic field direction over here is like this B with respect to one of the currents. The magnetic field with respect to the other current, if I take it as B like this, if I just draw one normal there, what you find is when this angle is alpha, this also will be alpha mathematically. This also will be alpha mathematically. So when you know these 2 angles are equal, when B is the magnetic induction due to one of the currents, what would be its horizontal component? B cos alpha. And exactly in the same manner, its vertical component will now be B sin alpha as such. Exactly in the same manner, for this value of B also, this directional component will be B cos alpha according to the value that is angle given. And in this direction, it will now be B sin alpha. So what we should understand here is B cos alpha and this B cos alpha due to these 2 magnetic fields which have been produced at that particular point P. These 2 components are equal and opposite. Then automatically these 2 are going to be cancelled. They are equal and opposite. So at that particular point P, due to the horizontal component, resultant magnetic field would be 0. Then what is left over, you check it. only vertical component of both the fields are in the same direction. Therefore, they are supposed to be added up. So, what will now be the resultant field over here? B resultant. This automatically becomes B sin alpha plus B sin alpha. This is what actually we people are going to get in this particular problem number 21. B sin alpha plus B sin alpha, that now becomes 2B sin alpha as such. But in reality, we all know very well what is the magnetic induction due to a straight conductor carrying a current at a distance, say at a point which is at a distance A. So, what will now be the formula there? You can now write this one twice. What is this value of mu? B. Mu naught by 2 pi into I by R. What is the current that is passing as given us? It's given capital letter I, that is the current, by R is the distance which is to be written as A. So, this is the formula for magnetic induction due to the current passing through a straight conductor at a point which is at a distance A from that conductor as such. But the point next is, what is this sin alpha? Look at this particular triangle, either the upper one you take or the lower one you take, no problem. What will now be this sin alpha? Opposite by hypotenuse. Opposite value is D. Hypotenuse value is A. So, in place of that sin alpha, I now can write D over A. So, simplify this one now. To write the resultant, 2 getting cancelled here, you are now left with mu naught I D by pi A square. This is the outcome. Whatever the result we people have got here at that particular point has now been mu naught I D by pi A square. Look at the 4 options now. The 4th option which has been given over here is exactly the same one what we have calculated. See the first option given, mu naught I D by 4 pi A. That's not the right option now. Mu naught I D by 2 pi A, the second option, even that also is not correct. What has been calculated here is very much before you. It is mu naught I D by pi A square, that exactly is in coincidence with the 4th option which has been provided to us. So, mu naught I D by pi A square, thereby we can say the correct answer for this particular question is D, the 4th option that is going to be correct. So, one of the good models what we have here, usually straight current carrying conductors means the general way of asking a question, every one of us we know, either where will the null point be, or what would be the force between them, or what would be force per unit length that is acting on one of the wires due to the other. So, these types of questions generally we expect, but here slightly a different one. We people are having now here 2 different rather straight conductors, parallel conductors, separated by a distance 2D, carrying the same amount of current, everything similar. The point has been taken somewhere at equal distances from both the strings or both the wires, carrying currents like. What is the value of magnetic induction at that point? That is a question what has been asked, and this is the calculated value one has to remember. So, the correct answer for this problem number 21 is going to be D according to the options provided to us. Now, the question number 22. This problem also is one of the excellent model questions what we have. A conductor of length L and mass M carrying a current I is placed on a smooth inclined plane making an angle theta with the horizontal. a magnetic field B is directed vertically upwards, then for equilibrium of the conductor, what is the value of tan theta? So he is asking you, for equilibrium of the conductor, tan theta is given by 4 options he has mentioned. One is the first option, BIL by mg. The second option over here is mg by 2BIL. And third option is mg by BIL. And fourth option is 2mg by BIL. Now let us check what exactly that's going on here. He is talking about a conductor of length L and mass m carrying current I is placed on a smooth inclined plane making an angle theta with the horizontal. Let us just check that. There is an inclined plane this way, having this angle as theta. It's a smooth inclined plane, thereby no need for us to think of friction over there. Now the body has been mentioned over here. This is the conductor. And what did he give about the parameters of this particular conductor? He said its length is given as L, mass is mentioned as m, current that is passing through that conductor, let us take it as I. He has given in the problem. Now the question is, when this is having a mass m, what would be its weight actually? We all know very well, weight directly acts towards the center of the earth, vertically downward. Now mg will be the weight. Normal reaction that's going to act this way. This is now the normal reaction. When I just extend this line of weight on the other side, mathematically this angle becomes theta. You can better understand that one. Now let us write the components of this normal reaction acting on this conductor. One component along this direction will be n cos theta. The other component along this direction will be n sin theta. So when n cos theta is acting against mg in this particular figure, n sin theta is acting this side. And what one should understand here is, for equilibrium of the conductor, in reality, we know very well equilibrium condition for any body is that sigma f must be 0. The algebraic sum of forces acting on that particular body must be 0. That is the condition for equilibrium of any body. Now even in this case also, same is supposed to be considered. Now this weight is compensated by normal reactions component. N cos theta and weight both are equal but opposite by directions. They get cancelled. Okay, fine. But what about this n sin theta? N sin theta is acting this side. There should be some other force due to magnetic field acting on this conductor that is supposed to be along this line. When that force is compensated by n sin theta, then there is a possibility for that conductor to be in equilibrium. So what can we understand now? This F must be the force due to magnetic field on a current carrying conductor of length L carrying a current I. So you can all understand well, F must now be BIL. That is the concept. Now these two are supposed to be equal and these two are supposed to be equal. So what I can write now directly? N sin theta from this figure must be equal to BIL, where B is the magnetic field applied, I is the current passing through the conductor, and L being its length as such. Now, the second equation what I can write is n cos theta, that now must be equal to mg. These two are supposed to be equal and opposite. These two are supposed to be equal and opposite. Overall, we now can write that tan theta, if you divide first equation by the second, then tan theta will be BIL, right, divided by mg. This must be the equation for tan theta. So, BIL is the force due to magnetic field acting on the conductor. Mg is the weight of that conductor what has been taken up. So, tan theta must now be equal to BIL by mg. That must be our answer. Of course, if you look at all the four options provided to us, very first option is BIL by mg. So, what can we write now? The correct answer for this particular problem is going to be A now. BIL by mg, that is the formula. In fact, for tan theta, that only he is asking us in the form of a problem here. So, only thing you should understand is what are the possible forces they are acting on that current carrying conductor, and what are their individual directions, and what is the condition for equilibrium? It is sigma F must be 0. That is algebraic sum of forces acting on a particular body. If it is 0, then one can say that the body will be remaining at equilibrium. That is the concept. So, if you just correlate all those 3 points, directly you will be getting for tan theta a formula like BIL by mg. The correct answer for this particular problem number 22 is A, according to the 4 options provided to us. This is problem 22 for us. Problem number 23 now. A cell is connected between the points A and C of a circular conductor ABCD of center O. Angle AOC is equal to 60 degrees. If B1 and B2 are the magnitudes of the magnetic fields at O due to the currents in ABC and ADC respectively, the ratio of B1 by B2, the ratio B1 by B2 is how much? One of the excellent model questions again. He is asking you what is the ratio of B1, that is magnetic field due to the first part of the circle, and magnetic field due to the remaining part of the circle. What is that ratio? B1 by B2 is how much? First option he has given us 1 by 5, and second option he gave us as 6, that is 6:1 like ratio. Third option he said 1, that means 1:1, that is the ratio he is talking about, and fourth option is given 5. So, obviously you can understand it's 5:1 like he is giving us. Out of all the 4, which is the correct option, we have to decide. Before taking up that one, let me just draw the circuit or the figure what has been given. It's in fact a circle he has given like this. And he has just marked 2 points over here. Those 2 points only he has just given, one as the point A and one as the point C. And this particular point he said as B, ABC, that is one part of the circular current carrying conductor what has been given there. Now, this particular part he has given it as ADC. So, ABC is one part, ADC the other part. What else he has mentioned? This total system now is connected across a cell like this. That's what has been mentioned there. And in reality, we don't require what is its value. He also has not mentioned, it is simply V, like you can write. That is potential difference applied across a system is V. That is the concept. And what is he giving us? There is a point here as O, which is now the center. He gave this angle as 60 degrees. And he has given one more point here, that is the current that is passing through the upper portion of this circular conductor, that has been given as I1, and the lower part of this circular conductor, the current whatever is passing is I2. So, this is the figure what has been provided to us. O is one point he gave, and of course I1 and I2 are the currents he said, and of course the total current that is entering, you consider that one as I ampere. Even if I give 1 ampere, 2 ampere also okay, don't worry about that, it is one and the same, like this is now I ampere. What is the magnetic induction due to the current passing through ABC at O, and what is magnetic induction due to the current passing through ADC at the same center, that is O? One is given as B1, one is given as B2. What is that ratio he is asking us? What is B1 by B2 is the question. So, first and foremost, you should understand one point. After reaching here, current is divided into two parts, no doubt. But these two values of currents are not going to be equal. Reason can be better understood straight away this way. If both the lengths of these parts are equal, then surely their resistances will be equal, and currents passing through them also are going to be equal. But here it is not so. This length is more than this length. So, common sense says this resistance will be more than this part of resistance. When resistance is more in this ABC part, then current automatically will be reduced there. How much it will be? Certainly less than this I2. So, what you should first of all understand here, the resistance of ABC, since it is greater than the resistance of ADC, what can I write now? I1 will be less than I2. That is my first observation looking to this figure. You can also easily understand that point, it's not a big task. So, first and foremost, to calculate magnetic induction, we can calculate the values of currents in terms of resistances. That is a concept. So, in reality, magnetic induction at the center of a circular current carrying conductor, that is mu naught by 4 pi I by R into phi. Phi is the angle. You can certainly understand that this is the formula actually. Now I can write the same this way. If I write what is this phi? This angle I take it as phi. What is this amount of current that is passing? You all know, I1. This I consider it as B1. So how to rewrite this one, you see now. I now can write the same this way. B1 is equal to mu naught by 4 pi I1 by R into what is actually this phi over here? Total angle is 60 degrees. That of course we write that one as pi by 3. Now what is remaining there? 300 degrees is remaining. So you can certainly understand in terms of degrees, if you want to write like that, you can write 300 degrees. Or else you can even write that one 2 pi by 3, 2 pi by 6 is going to be 60 degrees. So 5 by 6 times 2 pi. That of course you can write like this directly. 5 pi by 3 we can write. So this one now will be 5 pi by 3. So this is my first equation. And what is this B1 officially? B1 is nothing other than the magnetic induction at this point O due to the current passing through ABC. That is what actually we people are writing that one. This is B ABC. That is what I am calling it as B1. Now exactly in the same manner, you try the second one, B ADC. I write this one as B2. That again can be rewritten mu naught by 4 pi into I2 by R till that extent, okay, into angle, that is pi by 3 I can directly write. This I take it as the second equation. So hope you might have followed this particular equation and this one as well. Formula is same, only phi that is variable. There phi means 5 pi by 3. Here phi is already given to us, that is pi by 3, 60 degrees we can understand. Now his question is, what is B1 by B2? Look at first. Mu naught by 4 pi gets cancelled, R gets cancelled, pi by 3 gets cancelled, I be getting 5 I1 by I2. But all of you can understand here, R1 is to R2, in this case, is 5 is to 1. How come? This is total 6 parts I am considering, 6 parts, total angle is 360 degrees. This is 60 degrees. What is remaining? 300 degrees is remaining, that is actually the angle covered by the remaining part. Therefore, 5 is to 1, I can write the resistance values. This implies what would be the ratio of currents now? Is it not 1 is to 5? So you can certainly understand resistances and currents are inversely proportional to each other when potential difference remains constant. Here you can all understand this portion and this portion, these two resistances are connected in parallel. In parallel circuit of resistances, potential difference remains constant. When potential difference remains constant, automatically we can write current ratio will be reverse ratio of resistances. So R1 is to R2, when I write 5 is to 1, I1 is to I2 will be 1 is to 5. Substitute that value over here please. Therefore, B1 by B2 is equal to 5 by 1 into I1 by I2. That is actually equation. What can I write now? 5 by 1 into 1 by 5. So 5 getting cancelled, 1 getting cancelled, what is left now? 1. So simply speaking, that ratio would be 1 is to 1. 1 is to 1 option is check that one. In the third option he gave it as 1. So straight away our answer must be the same. So what is the correct answer for this particular question, please? The answer is simply C. So what you people have to understand in this case is how the currents are being varied depending on their resistance values. Because these two resistances, in this case you can understand they are in parallel. When resistances are connected in parallel, we can understand the potential difference remains constant across them. Potential difference across the first resistor, across the second resistor, both are equal. When V is same, then I and R are inversely proportional to each other. Considering the same concept, you can now solve the problem this way. So what is that value over there? Simply is asking you the ratio, therefore it is 1:1. Suppose if they ask you what is going to be the effective magnetic field, then you just apply right hand thumb rule, it's going deep into the board. Here also right hand thumb rule if you take, it is coming outside the board, both are equal and opposite, therefore the resultant field will be 0. But he is not asking you resultant field here, he is asking you simply the ratio. Therefore, since both are equal in magnitude, 1:1 must be the correct ratio. That is what you have to understand for this problem number 23, what we people are having in this order. Let us check the problem 24. Two long straight wires are connected by a circular section that has a radius r as shown in the figure. All segments of the wire lie in the same plane and carry steady current I. The magnetic field at the center O of the circular segment is how much? Once again the options are given this way. The first option says mu naught I by 4 pi r, and second option says mu naught I into beta by 4 pi r. Beta of course has been the angle given there. And third option says beta mu naught I by r. And fourth option beta mu naught I by 2 pi r. What is the actual figure he has mentioned? Look at. If you can identify that figure carefully, calculation is very simple. But a wonderful model question here we have. There is a conductor this way. There is a circular part for the same conductor. There is a straight conductor this way also. Now extend this conductor back, extend this conductor backward. This is the point O what he is talking about. And he said in the problem, current I is just entering this way and leaving the system like this. And he has mentioned us that this angle what actually the system in this curve is making with this point, that is given as beta. Another thing what he has mentioned is the distance to this curved part to this point, that's given as r. In fact, you people can certainly understand r is going to be the radius of this circle, of which this small portion is a small arc. So that is actually what he is talking about. So figure has been given this way. The current of course he has given capital letter I, or small letter whatever it is, it hardly matters for you. So whether you take this small I or capital I here, or even here also capital I, here also capital I, that hardly matters for us. Concept you should understand first. Look at carefully. This conductor, when I am extending it, I am just getting that conductor is touching this point O. So you can surely understand that this point O is right on the conductor. Then you can understand well there will be no magnetic field at that point due to the current passing through the conductor. So you can certainly understand this portion, whatever we have here, that will never produce any magnetic field at O. So leave that. What about this part of the conductor now? Again, when you are extending it, it's coming and touching at the point O only. So what again you can understand? If I consider this is the conductor, like the point lies again on the conductor. Point is lying again on the conductor means certainly you can understand that also can never produce any magnetic field over there. So magnetic field produced due to this portion at the point O will be 0. Magnetic field produced due to this portion carrying current I at this point O will be 0. So the current passing through this part of it and this part of it will never produce any magnetic field at this point O. So you need not calculate anything about this part and this part now. But with respect to what we have to calculate? With respect to this curved portion, we just have to think of what is the magnetic field that is produced at the point O. And how much angle the curved part is making. It's very clearly mentioned in the problem that it is beta. Then what would be the magnetic induction at this point O now? B at O, I just want mu naught by 4 pi into I by R into phi, that is actual formula. Mu naught by 4 pi into I by R, that is the current that is passing through that one, and R is the radius. I by R into the value of phi, that's what actually is the formula we have to apply. Now what will be its value you look at now? This implies B is equal to mu naught by 4 pi. I, of course, he gave capital letter, by R into what is the angle it is making, he said, beta. So what must be your correct answer now? Mu naught I into beta by 4 pi into R. The same, of course, he has given the other way, this way, beta mu naught I by 4 pi R. That is the option he has given. So what is the correct option now here? It is the second option which is correct, mu naught into I into beta by 4 pi R. So the correct answer for this particular problem is going to be B now. So only thing you should understand from this entire description is this: whether there is a magnetic field due to the current passing through this straight conductor or not. Observe that. Similarly, whether there will be a magnetic field produced due to the current passing through this portion of the conductor or not, you identify. Here the magnetic field produced is 0. Due to this current also 0. Only this portion you people have to evaluate. Take that arc of radius R, finalize the magnitude of the magnetic field that is produced at the point O due to the current that is passing through that circular arc. So the correct answer for this particular problem is going to be B according to us. The next number is 25. A current I flows in the network shown in the figure. Resulting magnetic induction at the point P is how much? Of course, 4 options have been mentioned once again. First option is mu naught I by 4 pi A. Second option is minus root 2 times mu naught I by 8 pi A. And third option is minus 8 by root 2 times mu naught I by pi a. And fourth option is 2 mu naught I by 8 pi a. But a figure has been given for this one as well. What is that figure? Try to first of all understand. There is a straight conductor this way, he said. There is another straight conductor this way, he said. This is in fact like a square. Till this extent, okay. Now here, look at the way he has just given us the total conductor. Truly speaking, this is completely a square. Of what size? The side length is given 2a. Even this also you can take this one as 2a. Now this side length is a. This one is also a. And he said this is the point P. That is the point of consideration given in the problem. And what is the direction of current that is passing through the system? He has given, you understand. This is the direction of current here. It's like this here. And this particular portion is carrying current up like this. And here the current is going horizontal this way. Here it is going vertical this way. Here it is coming horizontal this way again. So this is the direction of current. Now one thing you should understand from this entire system now. With respect to this part of the conductor and this part of the conductor, what is the magnetic induction at that point P? You estimate first. Let us take these points as well. This is A, this is B. This one you can take it as C. It is also mentioned there. And of course this point is given as D. This is given as E. And this one is given as F. So first you calculate what is the magnetic induction due to this straight conductor AB and due to this conductor BC. Certainly you can understand now, if I just join this point with this point P, you will be getting exactly 45 degrees angle there. So apply the concept of magnetic induction at a point due to a finite long straight conductor. A conductor of finite length I am talking. There is a formula which all of us we know, mu naught by 4 pi I by R into sin phi 1 plus sin phi 2 or sin alpha plus sin beta, whatever you write. Same formula we are going ahead now with. So take this part and this part first. If I just take, this is the direction of current, it's coming out over there at that point P. Even for this current also, it's coming outside the board. So the direction of current at that point P due to AB and BC, both of course are coming out at that particular point P. So outward magnetic field is produced. What is the formula? Now I can say directly BAB. That is another one BC. These two are equal to what? They are equal to, this implies, this I write it as B1 now. B1 is equal to mu naught by 4 pi I by R. R is going to be 2a, the distance, into one angle will be 0 degrees and another angle will be 45 degrees. So you can straight away understand this one, this is equal to this, no doubt. So B1 is this much. How much its value will now be? B1 is equal to mu naught by 4 pi into I by 2a into 1 by root 2. But truly speaking, this is creating or producing one magnetic field there, this is producing another magnetic field there. Both the currents are producing two individual values. Both are equal. But what will be the resultant? So, the resultant magnetic field will become 2b1 here. b1 due to this one and b1 due to this current as well. Both are in the same direction, they are producing the magnetic fields. Therefore, we can add them. So, what is it you are getting now? 2 times. Now, 2 gets cancelled. You are left with mu naught by 4 root 2 pi into I by A. That is one resultant due to BC and AB. What is the direction now? Outside. Direction of magnetic field is outside. So, that is one point you have to understand. Now, come across this portion. Due to DE and EF. Look at, observe, right hand thumb rule you apply. Won't you find that the magnetic field is going deep into the board now? Due to this particular current and due to this particular current also, it's going inside. So, I have to calculate those two fields and add them again. So, what will now be the next point? That is, magnetic field due to DE and magnetic field due to EF, both are equal to B2 each, if I write. Then what is that formula now? This implies B2 is equal to mu naught by 4 pi into this time I by the distance becomes A only, not 2A, into once again sine of 0 plus sine of 45. Same formula almost, excepting this 2A and here A, no other difference. And another difference is the direction of the magnetic field here outside, here into the board. That's all is the only major difference you are observing. So, what can we write now? This becomes 1 by root 2. So, this now becomes is equal to, directly I can write mu naught, right, I by 4 root 2 into A. But what I just want is, what is the resultant of these two fields now? Resultant of these two fields means 2b2 I should write. Now 2 if you multiply with mu naught I by 2 root 2 A, I will be getting. This is the resultant magnetic field due to DA and EF. What is its direction? Direction is into the board. Now you can see one is outside, one is into the board. Both are opposite. Then how do we get the effective magnetic field? Effective magnetic field means a very simple concept you people can understand straight away. It is now 2b1 minus 2b2. That's all. This is 2b1, this is 2b2, subtract one from the other. What will you get now? You will be getting this value, right, like minus, because this is 4 root 2 here in the denominator. Right, in the denominator we will be having 4 root 2. Of course, one more pi will be here. We just have to take. Even here also, one more pi we people have to write. This is 2 root 2 pi, here 4 root 2 pi. So, definitely this value will be less than this value. So, effective value when you take the difference, you will get a negative sign there. Sure, okay. What you will be getting here? Mu naught I by pi A will be common. You will be getting mu naught I by pi A. Till this extent, okay. What is this denominator here? You are going to get 4 root 2 you will get. you will be getting mu naught I by 4 root 2 into pi into a with a negative sign. But of course, that option has not been given directly in the same form in the problem. See the second option. He gave minus root 2 mu naught I by 8 pi a. He gave. That root 2 cancels in 8 for root 2 times. So this is as well equivalent to root 2 by or root 2 mu naught I by 8 pi a with a negative sign. That is what has been given in the problem. So what is the correct option over here? The correct answer for this particular question is going to be B now. So whatever B given is this, that also can be rewritten like this. Simply take the difference of these two and finalize your answer. One of the good model questions we have, only thing you should understand is how to apply the magnetic field at a point due to a straight conductor of a finite length. That you have to understand. Mu naught by 4 pi I by r into sin alpha plus sin beta. Those alpha beta values, if you can identify them carefully, resultant will be just like that. It's not a problem. So the correct answer for this problem 25 is the second option. Probably all of you might have understood how to just tackle this type of a model here. That is problem number 25 we have. Let us check 26th problem now. Two particles x and y having equal charges after being accelerated through the same potential difference enter a region of uniform magnetic field and describe circular paths of radii r1 and r2 respectively. The ratio of mass of x to that of y is how much? So first particle is giving as x, its mass we are taking it as mx. Second particle is taken as y, its mass is taken as my. Then what is mx by my? That ratio he is asking. And see the options given over there, r1 by r2 whole power half. That is the first option. And second option is r2 by r1. Third option is r1 by r2 whole square. That in other words r1 square by r2 square also you can write. And fourth option says r1 by r2. So this particular question has been given in one of the IIT papers earlier. So two particles x and y having equal charge after being accelerated through the same potential difference enter a region of uniform magnetic field and describe circular paths. So when they are describing circular path, we can understand centripetal force due to the magnetic field must now be equal to centrifugal force that is acting on the same particle. Centripetal force is due to magnetic field BQV and centrifugal force is mv square by r. Now out of that one velocity I can cancel. Now you can rewrite the same this way, BQ is equal to mv by r. But all of you can understand straight away mass into velocity is linear momentum. It's represented by P. That now can be rewritten like this as under root 2m into kinetic energy divided by this radius. Linear momentum is equal to square root of twice the mass of the particle into its kinetic energy. The relation of course is known to us all. Same formula I rewrite in a different way. Look at 2m into what is the energy gained by a particle when the potential difference applied across that particle in the form of electric field is V. So what we should write here, it's now QV. Q being the charge and V being the potential difference. Energy gained by a particle entering an external field having a potential difference capital V can be written as QV. That divided by the radius. So I can now write what is the formula for radius according to this. Root of 2m into QV by BQ. So observe this equation carefully. Now while reading the question, you all can understand both the particles have equal charge. So Q is constant for both of them. And being accelerated through the same potential difference. So that means potential difference must be a constant over there for both of them. Enter a region of uniform magnetic field. That means even magnetic field into which they are entering also is going to be the same. So B is constant for both of them. Q is same for both of them. V is same for both of them. And we know well 2 is going to be a constant anyhow we know. Now what is remaining? R is proportional to root m. That is what has been given there. R is proportional to root m. Now the question is, what is mass of the first particle mx? Can't I write it is proportional to r1 square or rx square? What is rx now? Radius of the circular path traced by the first particle x. And what about the second one? Similarly, mass of the second particle y is directly proportional to ry square. That is radius of that particle which has been given as y square. Radius of the circular path traced by the second particle, I am taking it as ry. Now if you take the ratio, you can say mx by my is now going to be r1 square by r2 square. Because he has mentioned there the radius of that curved path or circular path traced by the first particle is r1. Of the second particle is r2. Then what should be your answer then? Mass of the first particle x by mass of the second particle y must be equal to r1 square by r2 square. That itself you can write r1 by r2 whole square also. So which option that is correct over there? The correct answer for this problem is going to be C there. C is given that the ratio of their masses of x and y, that ratio is r1 by r2 whole square he gave. That is as well equivalent to r1 square by r2 square. So this is the correct answer for this. Only thing you should understand here is this type of a conversion. Momentum can be written under root twice mass into kinetic energy, and kinetic energy gained by a charged particle when it is entering into an external field having a potential difference capital V is going to be QV. That formula you need to have in memory here. So if you know that one, direct the ratio you can calculate. It's not a big task here. So correct answer for this problem 26 is going to be C as such. That is problem 26 now for us.